Hello students, in this video we'll see an example of using the change of variable theorem in higher dimensions. I'd like to find the double integral over the elliptical region x squared plus 4y squared is less than or equal to 1 of the function cosine of 9x squared plus 4y squared dy dx. And so we have this elliptical region. So what does this elliptical region look like? Our region in the xy space, here's x, here's y. Well, if I plug in x equals 1/3 and y equals 0, that would be in the region. So I have 1/3, 1/3, and negative 1/3 is our minor axis. And if I plug in y equals 1/2 or y equals negative 1/2, that will be the length of my major axis. So we have a 1/2 for y and then negative 1/2 for y. And I get this elliptical region over here. So this is the interior of an ellipse, is our region over here. And so it's very difficult to integrate over ellipses. So what I will do is I'm going to change the coordinates. I'm going to introduce a coordinate change. What we're going to do is I'm going to let u be 3x and v be 2y, which is equivalent to saying what? Which is equivalent to saying that x is equal to u over 3 and y is equal to v over 2, right? So these are equivalent statements over here. And so let's recall our change of variable theorem. Our change of variable theorem so that the double integral over a region E of f of xy dx dy is the double integral. My limits of integration are going to change to a new limit of integration, d, and I'm going to have f of some function a of u and v, b of u and v. So my x's turn into a of u and v, and my y's turn into b of u and v. And then we have what? Then we're going to have the absolute value of the determinant of this Jacobian matrix, which is partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v, du dv. So my limits of integration change, my variables x and y change, and my differential changes according to this Jacobian rule. Okay? So let's find what this Jacobian is going to be for our problem. So in our problem, what will the Jacobian be? I'm going to have to find the determinant of partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. In this case, it simplifies dramatically because partial x, partial u is going to be 1/3. Partial x, partial v, there is no v in x, so that's going to be a 0. Partial y, partial u is going to be 0. There's no u's in y, and partial y, partial v is going to be 1/2. So if I do this determinant, I get 1/3 times 1/2, so I get 1/6. So my dx dy is going to turn to the following. My dx dy turns into 1/6 du dv. So let's do our change of variable. So our integral over here will be equal to, what's my region of integration? Well, if 9x squared plus 4y squared is less than 1, what does that tell me about u? Well, u squared is 9x squared. V is 4y squared, so u squared plus v squared is equal to 9x squared plus 4y squared. So u squared plus v squared is less than or equal to 1 in our new limits of integration. So my region turns from a what? My region turns from an ellipse into a circular region. I'm going to have the cosine of what? The cosine of u squared plus v squared. Then I'm going to have a 1/6 du dv. Now, that's great because I can take this integral over here and put it into polar coordinates, right? So I'm going to do a polar coordinate change of variable. So this is the interior of the unit circle. So my angular variable theta goes between 0 and 2 pi. My radius goes between 0 and 1. I'm going to have the cosine of u squared plus v squared. That's the equivalent of the radial variable r squared. So that's the cosine of r squared. Then I have the 1/6 from the transformation. And then du dv is going to transform into r dr d theta. That's the Jacobian and polar coordinates. So I have an r dr d theta. I can rectangular separate this and write this as 1/6, the integral from 0 to 2 pi of just a d theta, times the integral from 0 up to 1 of r cosine of r squared dr. Now we're almost done because this is going to integrate to 2 pi over here. So these first two terms turn into a what? Turn into a pi over 3. And then how am I going to do this integral over here? Well, I can do one more substitution. Or I can just say that, just conjecture what this is going to be. Because the antiderivative of cosine itself is sine. So it'd be sine of r squared. So if I had a 2r and a 1/2, that would balance things out. So I'll put a 2 over here and a 1/2 over here. Then this is going to be the perfect derivative. It's the derivative with respect to r of what? Of the sine of r squared. We can check that because the derivative of sine is cosine, and the derivative of r squared is 2r. So this will turn into a what? This will turn into a pi over 3 times 1/2 times the sine of r squared evaluated from 0 to 1. The sine of 1 stays around, the sine of 0 is 0, so this total, the final answer will be pi over what? Pi over 6 times the sine of 1, and there's the solution to the problem. Thank you very much.